Welcome to week 3 of discrete mathematics. The subject of this section is the description of some more algorithms for arithmetical functions. That means systematic ways of computing things. We've already seen one such algorithm, namely to express an integer in binary form, converting from base 10 to base 2. Today, I'd like to describe a means of taking one integer to the power of a positive integer, raising an integer to an exponent. And we'll try and do that in a way that's more efficient than the sort of naive way of doing the exponentiation, as it's called. And then in the next subsection, we'll be talking about Euclid's algorithm, which I expect most of you know about. That's one of the first algorithms conceived of. I'm not going to talk as such about section 3.1. Let me just make some remarks about what's in the notes in section 3.1. I think in that section I really try and explain that there's often more than one way of computing something, or one way of formulating an algorithm. So I use the example of n factorial. And how would you compute n factorial? Well, in the last section we needed 7 factorial, and the sort of way that was computed was to just start by doing the multiplication. So you start with 1, which you can forget about actually, you multiply that by 2, you multiply that by 3, you multiply that by 4 until you have to stop, so up to 7 in my case. That's, if you like, computing factorials by what's called iteration. You just keep iterating some operation. It's very straightforward, very simple. It's not necessarily the best way to do something, though. Another way you can think of computing n factorial is to somehow, if you've already computed, say, 6 factorial, you know that to get 7 factorial, you just have to multiply by 7. So it's useful to know the recursion, the recurrence formula, if you like, for n factorial. It's simply n times, obviously, n minus 1 factorial. And in a sense, this way I'm working backwards. Here I was sort of adding on or multiplying on from the right these more and more higher and higher numbers, integers, successive integers. This time I'm in a sense working backwards, and this would be computing factorials by recursion, as I say, related to the recurrence relation for which is this 4 factorials. An, if you like, is n times an minus 1. Now, in the case of factorials, it doesn't make too much difference what method you use, but in other situations it will. And in particular for the Fibonacci numbers, there's really a big difference in these two methods. And the simplest, the sort of quickest way to compute Fibonacci numbers is really by iteration. But to see exactly how you do that, I refer you to sheet 3, this week's sheet, question 4. Whereas computing Fibonacci numbers by recursion is sort of the way you define them, but it actually leads to much more complicated data structure. Anyway, the other thing I mentioned in section 3.1 is asymptotic notation, because if you want to know how many operations are needed, one needs to know for large, for example, if n is very large, how many operations we need. So we need to sort of comparison between sequences. So just to remind you, if you have 2 sequences and we say that a sequence an is big O of bn, I'm just really doing the individual terms, as n goes to infinity, this means, remember, I'm sure you'll have come across this, it means that the quotient, assuming bn is not always 0, an divided by bn is bounded as n tends to infinity. Or what's the same difference? The absolute value of that is bounded as a positive number as n goes to infinity. In section 3.1, I also mention something that's less commonly used by mathematicians, but used by computer scientists. The notion, I'm not going to write it all out here, but the notion of A is capital theta of B. That simply means that A is big O of Bn, An is big O of Bn, and Bn is big O of An. So it's more symmetric, sort of equivalence relation between sequences, and it's a stronger situation would be when An is what's called asymptotic to Bn, which means that the quotient tends to 1. This obviously implies the theta relation. But I'm not going to say anything more about that. We'll be using mostly big O, but you may need this if you go into it in more depth, for example, if you do an informatics module. So that's all I want to say about section 3.1. Please look at the notes, try and understand the sort of computer code I've written, because it's very simple. You can play with it online if you want to, but it's not necessary. The main topic then for today is how to exponentiate, as we say, take an integer or number to the power of another positive integer. So this is 3.2, and the idea of this is to use a method which isn't immediately obvious. To make things more efficient, we compute exponents by what's called repeated squaring. So the point is, let me explain this with an example. Same example from the lecture notes. So I want to choose a real number. Well, I mean, for simplicity, it would normally be an integer. So let x be normally a positive integer. Let x be a positive. Well, let x be an integer, let's say. We want to compute, or I want to compute, in order to explain to you the method. We want to compute some power of this number, and the one I've chosen is x to the power 19. The power I've chosen is 19, just as an illustration. So what is x to the power 19? Well, if we just want to compute this naively by iteration, we start with x, we multiply that by x, we multiply that by x, we keep going. I mean, in a sense, there are brackets here, but we do the first multiplication, then we do the second multiplication, and so on. And eventually, we want to have 19 x's in this row. How many multiplications do we have? We have 18 multiplications. 18 multiplications. So there are 18 operations here. So 18 ops. That would be the naive way of computing x to the power 19. So if you have a calculator like on a mobile phone that doesn't have powers, you would have to sort of use, one way would be to do it this way. However, let me explain now with this example, as I do in the notes, how you can actually reduce the number of operations rather quickly, rather simply. And this relates to the binary expansion, actually, of 19. So we take, as I'll explain in a moment, but let me just say it this way first of all. We take x to the 19. First of all, it's a bit of a nuisance because 19 is an odd number. So the first thing I do is think of it as x to the 18 times x. And x to the 18, being an even number, is the square of something. So x to the 18 is x to the power 9 squared. And then we have to add on the extra x, or multiply by the extra x. So obviously x to the 19 can be written like that. No one's going to dispute that. Now 9 is also odd, so we do the same thing, sort of recursively. So x to the 9 is x to the 8, which is x4 squared, x to the 4th squared, times the extra x to get x to the 9th, and that's all squared again, times x. Same thing. Now we've almost finished. X to the 4th, that's an even, 4 is an even number, so it's a bit easier. So it's x squared squared, that's x to the 4th. Then we've got to square x to the 4th. We've got to multiply by x. We've got to square all that. And we've got to multiply by the final x to get the 19. So that's another way of writing x to the 19, but you see the advantage of this. How many operations have I used here? I've started with x, whatever that may be. I've squared it, that's one operation. I've squared again, 2. Squared again, 3. Multiplied by x, 4. Squared, 5. Multiplied by x, 6. So that's only 6 operations. 6 multiplications, effectively, because a squaring is a multiplication. So I can actually compute x to the 19 with 6 operations, and if you have to do that on a mobile phone, that would be much quicker. Now the question is, I'm hiding a bit of work here because I'd have to know how to write the 19 and you know, somehow go from the 19 to writing this like that. How do I do that? It's going to need a bit of time to understand how to do that. Well, what I want to explain to you now is that really what I'm doing, all I'm doing is using the binary expansion of 19. So you see 19 is equal to base 2, it's 1, 0, 0, 1, 1 in binary. Because what is this telling you? This is 1 unit plus the 1 here represents what, 2 to the power 1. No 4s, no 8s, and then there's a 16. So I'm just saying 19. I'm just sort of extracting the highest powers of 2 I can. I can extract the 16. That leaves me a 2 and a 1. So that's what 19 is in binary. And so if you think about it, the fact that 19 is an odd number, the 1 here reflects the fact, this 1 reflects the fact that 19 is an odd number, and it corresponds to the x here. Now, if I forget about that, if I forget about this 1, if I make this 1 a 0, then that's like getting rid of the x. If I make this 1 a 0, that's like getting rid of the x. If I completely forget about that digit there, that's made me a smaller number, which is actually like 9. This is the binary expansion of 9. That's like forgetting the squaring. You see, I am back, the exponent has gone back to 9 if I cover up the squaring. And so you go on, this 1 here corresponds to the x here. So you see what I'm really doing is these x's appear, these extra x's appear when there's a 1 in the binary expansion. Then the next one is a 0. That means that inside here we have no x. And inside this bracket we have no x. And then finally there's always going to be a 1 at the beginning. And that sort of corresponds to the fact we're always going to start with an x. So if you like, you could say that I started with a 1 here. I've sort of inserted a 1 in some sense here and then multiplied that by x. So there's a sort of 1. There's always going to be a 1 to start with. So you see how the binary expansion of the exponent, the power 19, has led to this way of giving a scheme to do the multiplication. Okay, now let me say the same thing using the table, because it's using the table that I would encourage you to actually do this, this process in practice in a more sort of systematic way, which is what an algorithm is. It doesn't have to be done by a computer. It's just a way of doing something systematically without really thinking. That's how I think about it. So I want to give you a way in which you can do things without really thinking hard. So let's do the same example, but let me express it in the form of a table. So let me remind you what we're doing here. We're going to compute x to the power 19. X is just some integer or some number. X to the power 19 by this method of repeated squaring. Let's say it like that. Exponentiation. Exponentiation means raising a number to some power. Doesn't necessarily involve the constant e. Exponentiation by repeating squaring. Oh, I should really make this correct. Repeated squaring. And multiplications at times. So that we first express 19 in binary. So we first express the exponent, which here is 19, what's called the exponent or the power in binary, in base 2 to base 2. And so what do? I take the 19 and I write it in binary, but with a bit more space than usual. So 1, 0, 0, 1, 1. That's what I've done. Now I'm going to form a table in which those binary digits are the heads of the columns. So I'm going to make this into a table with 3 more rows like this. And I'm going to label the rows, you'll see why in a moment. Start, square, times x, asterisk always means times x, if a 1 at the top of the column. And now I'll explain what I do. I'm raising 19, x to the power 19. So start actually means that I just start with a 1. So you always put a 1 there that just corresponds to this 1 here. And then I'll explain in a moment, we don't really need the first column, but to make it systematic and to make the method correspond to the binary expansion, I'm using a first column here. So I square the 1, which of course gives me 1 squared if you like. And I multiply by x if there's a 1 in the top of the column. Well, in the first column, there'll always be a 1, so this will always end up as x here. That's forced. That will happen in all cases. And then I go to the second column. This is really going to be a carry forward. So whatever is in the bottom of this column goes to the top of the next column. And then I keep going like that. So I square what's there, that's x squared. I ask, is there 1 or 0? There's a 0, so nothing happens. This stays as x squared. This gets carried forward to the top of the next column. This gets squared. There's still a 0, so that stays as x to the 4th. And the x to the 4th goes to the next column. That gets squared, x to the 8th. Now there is a 1 here. There is a 1 at the top of this column, so we multiply by a single x. So this becomes x to the 9, as we did on the previous page. The x to the 9 goes to the top of the next column. It gets squared. And then we have our final multiplication by x, because there's a 1 here, meaning that 19 is an odd number. And we end up with x to the 19, which is what we wanted. So that shows you how you get the x to the 19 by 6 operations. Essentially what's happened here is, although I showed you the first column to sort of be a bit more systematic, you can sort of forget about it. If you just remember that's how it goes. So you do the binary expansion, but you can sort of throw away the first digit, which is always going to be a 1, provided you remember to put the x in this position. And then how many operations did we need? 1, 2, 3, 4, 5, 6. 6 operations again, if we forget the trivial operation of the first column. Okay, so that's how I think of the method. I really just did the same thing as on the previous page, but I put it in a table, so when you do this in practice, you're less likely to make a mistake. You just, x may be a given integer, so x may be 17 or something, and you just do all these operations, filling out the numbers, filling out the entries numerically. Okay, now let me do an exercise now to explain this, and I'll still use the exponent 19. So, camera's a bit slow. So here's an exercise. Compute. Well, I'll actually give you 2 exercises in one. I'll only do the second one. 5, so x here is going to be 5, makes it easy. 5 to the power 19. I'm going to do modular arithmetic so that I don't have to sort of get my calculator out and do the big powers. I'm going to actually keep doing modular arithmetic. So I want to compute 5 to the power 19 mod 17. That's the first exercise. And the completely separate exercise is going to be compute 5 to the power 19 mod 16. Okay, now I've given both of these just to remind you the difference here. You see, in this case, the 17 is a prime number, so we can use Fermat's Little theorem. So we can use Fermat's Little theorem, which tells us that 5 to the 16 is equivalent to 1. You take the prime minus 1, which is 16, is equivalent to 1 mod the prime. And from there, it's quite easy. There's a slight gap here, but it's quite easy to deduce that 5 to the 19, you've just got to cube 5 and do that mod 17. It's going to actually be equivalent to 6 mod 17. So this example had nothing to do with what I was talking about today. It was just to remind you to use Fermat's Little theorem whenever you can. The real exercise is going to be this mod 16, because 16 is not a prime, and I can't ostensibly use the Fermat's Little theorem. So I'm going to do this by means of my table. So 5 to the 19 mod 16, we're going to do a table. So here's the table. I'm just going to repeat the 19, which has been written in binary as 1, 0, 0, 1, 1 again. And then I complete the table with 3 more rows. So I'm using mod, let me copy this down, it's been hidden, mod 16, this table. So we're going to, let's remind us what these, so the first row is a sort of start or carry forward row. Maybe I'll call it this time carry forward rather than start. And then the second row corresponds to squaring. That always happens. And then the third row is multiplying by x, which in this case is 5, if the column is topped by 1. So I'll put multiply by 5 question mark. You have to ask if there's a 1 there. But I'm going to forget about the first column now you've seen the method, because that was really just part of the theory in some sense. So we're not going to worry about the first column. Remember, what we do is we just put the x straight into this position. So the 5, x is 5, goes straight into that position there. It gets squared immediately, but we're working mod 16. So 5 5s are 25, that's 9 mod 16. Reminds you of Pythagoras' theorem, because 4 squared plus 3 squared is 5 squared. And then, is there a 1 at the top of the column? No, there isn't, so this stays as a 9. And then the 9 gets carried forward, goes back up here. It gets squared, 9 9s are 81, but 80 is 5 16, so 9 squared is 1 mod 16. It's very easy, actually. The numbers are very simple. This stays as a 1 because there's no, this is a 0. The 1 gets carried forward, it gets squared. Now this is a 1 here, so the 1 has to be multiplied by 5. And then the 5 gets carried forward, it gets squared, so that's 25, which is 9 mod 16 again. Now it's slightly different because there is a 1 at the top here, so we have to multiply 9 by 5. 5 9s are 45. 45, if you like, is twice 16 plus 13. So this is actually 13, and that's the answer. I could also say it's minus 3, if you like. It's 13 is equivalent to minus 3 mod 16. But anyway, the answer therefore is that 5 to the power 19 is equivalent to 13 mod 16. And that explains the method of exponentiation, in this case mod 16, by repeated squaring and other operations where needed. So I want to finish by answering the question, how many operations do we need to compute some number x raised to the power of a positive integer n using our method that involves repeated squaring. And I can answer this quite quickly. Let's suppose that the exponent n has, to express n, we need b bits. That is, n has, when we express it in binary, it has b digits, so b binary digits. Okay, so in the case of 19, so b is 5 when n is 19. In general, this implies that, this previous line implies that 2 to the b minus 1 is less than or equal to n, which is strictly less than 2 to the b. Because for 19, 19 is strictly less than 2 to the 5, but it's greater than or equal to 16. Any number in that range needs 5 binary digits. Okay, now the point is this: when we had our table, we used each column was labelled by a binary digit in the expansion of n. But we don't really use the first column. All the operations in the first column were trivial. 1 squared, 1 times x. So we can forget about those in practice. So really we had b minus 1 columns. So we used, in our algorithm, we used b minus 1 columns effectively. And how many operations does that require us to do? So the number of operations is at most. You see, we don't know exactly what we have to do for each column, but we always have to square. We may have to multiply by x. So if the worst scenario is when the binary expansion has all ones, and then we have to always square and always multiply by x. So that's the worst scenario. So in that case, we would need 2 times b minus 1 operations. Okay, now b minus 1, if you take logs here, b minus 1 is less than or equal to log to the base 2 of n. So this is less than or equal to, in fact it's the floor, this is twice times the floor of log to base 2 of n. Remember this notation in section 1, at the end of section 1, LG means log to base 2. And that's less than or equal to twice log n. These brackets here mean the floor, that's the biggest integer I can fit inside log to base 2 of n. So the conclusion is that the number of operations is of capital order, capital O, of log to base 2 of n. That's the final result, and it means that this algorithm uses what's called log time, if you can understand that each operation really, roughly speaking, will add to the time taken. This algorithm works on the basis of big O of log n, whereas if we used the iterative procedure of multiplying, we would need to just multiply x by itself. We would need n minus 1 multiplications. That would be big O of n. So this is really this, instead of the more naive algorithm, which would be big O of n, effectively. Okay, I'll stop there.